All right. So our next speaker is Professor Flora Salim. She's a professor at RMIT University, Australia. Her research interests include human behavior modeling, spatial temporal data mining, machine learning on stream data, and sensor data, and smart cities. Today, she's going to talk about learning compact representation with less labeled data from sensors. Professor Salim, please.
Thank you for the opportunity to give this talk. I'll just go straight to the next slide. There's a lot of sensors. I know we've all been working with sensors. I don't have to convert everyone on this talk. It's important to actually work with sensor data because it's all around us. But how do we actually then utilize the understanding of human behaviors, to actually inform and make our life more efficient, sustainable, and improve our health and safety? Now, the problem is a lot of sensors are deployed in the wild, but how do we actually use them to actually recognize different activities and different behaviors of human with heterogeneous sensor data? Now, the problem is, of course, everyone, there's so much sensor manufacturers, and they all have different data. There's a lot of data that's actually, they're not homogeneous, they're very dynamic. And the thing is, with regards to understanding human activity, recognizing human activities, there are some very well-established problems, such as recognizing physical activities, such as people standing, walking, running, jumping. These are already available on your mobile for active recognition API on Android, for example. There's also things like gesture recognition. And a lot of the focus that we're working in our group are basically the non-visual, basically time series sensors, multimodal sensors. But what I'm actually referring to also is actually more complex behavior recognition. So this behavior recognition can come from different sensors. So for example, you want to recognize people's emotion, you want to recognize people's tasks. If somebody's actually at work, are they actually having a meeting, doing a presentation at the moment? That means, for example, right now where I am, because this is online, I'm actually sitting down while I'm actually giving a talk, and I'm actually having gestures around my face. So this is actually, I'm giving a talk, right? So how do we actually recognize this certain behavior? And why this is important? For example, there's a lot of intelligent assistants these days. Right now, they're still trying to pull information from us to understand what is actually happening. So it's a very basic Q&A, but if this system can be more proactive by recognizing behavior, it could be more useful. What I'm saying about activity and behavior recognition in the wild means you can, there will be times and days in the future where your phone and sensor devices will not just be recognizing number of steps you're taking, but potentially and also maybe number of sleeps, but a whole wide range of other activities in the wild. Now, of course, then this actually requires a wide variety of inference tasks. I've mentioned physical active recognition, step counting, but in our lab, we've done all range of these tasks, including things like inferring whether somebody's concentrated, can concentrate well at work, how productive they are, trying to recognize whether somebody's doing unsafe or unsafe behavior, trying to recognize activities in the brain, and even health conditions, trying to understand their app usage in relation to their work, their tasks. Psychometric is what is someone's personality, what do they like, what they like to buy, for example, and things like that. Now, the problem with this though, representation learning requires lots of labeled data, and annotating the big sensor data is infeasible because this is really time consuming. You know that the collection of ImageNet that actually helps the boom of deep learning and computer vision, it's those millions of data was actually require annotation of over 7 years. So and those are just images, static images. And what about sensor data? Now think about the typical pipeline for behavior recognition in a daily environment. You need to actually set up the study to actually recognize behavior. Is you start often with sensor selection and then you deploy them. So you might choose to deploy environmental sensors and wearables and movement sensors, and then you collect the data and you do the manual annotation labeling. Then only you do pre-processing all that, although you can also do it on the device, and then doing the feature selection, and only you get to the fun part, which is the machine learning part. And then you actually deploy the model. Now, So in here, you could see a lot of bottlenecks basically on these first aspects. And also is having to annotate the need to annotate the data means people need to be observed, often using cameras in their natural environment, in, let's say, in aged care, or in a factory, or in let's say in a mining site, right? So all these different areas, because again, a lot of machine learning models these days rely on labels, and these approaches are typically fully supervised. So again, these are expensive because it requires domain input and too narrow or specific. Now, let's say, for example, if the sensors deployment are handled, right? So people are on their mobile all the time. They've got so much sensors on their mobile or wearables, and we can actually tap into it. Still, there's still major bottlenecks on data collection and annotation labeling. Now, how do we actually handle that? The problem also with the sensor data collected in the wild, if you're not the one who if you're not the one who's deployed the sensor, there's so much different manufacturer, different range of sampling range unit, frequency of collection, data being pushed to the cloud. The sensors may not be fully reliable. Some channels may be positively, negatively correlated. And if you actually get people to annotate it post hoc as a cross-sourcing approaches, for example, then, you know, there could be disagreement in annotators. And also the problem is it's not as easy as annotating images like in ImageNet, because you know, because the data is so noisy. Sometimes the changes in the sensors in one channel may not correspond to the changes in other channels. So, and there's a lot of bias in the distribution across different contexts, activity labels. So if somebody might be doing multiple activities, so one particular sensor may correspond to a physical movement, whether the other one may be corresponding more to an online or cyber behavior activity movement. Now, so I mentioned already, typical representation learning requires lots of label data. So how do we then get it? How do we actually work with sensor data if we don't have labels? So the thing about it is, think about what makes good representation from sensor data. Now, these are the ones that we come up with. So first, they need to be compact and representative. That means, because sensor data, you know, we want to make a representation that's basically deployable on sensor devices. So, I mean, I'm speaking again to the converter here. You know how important it is to make it efficient. And they need to be robust because of the noise and noisy environment and all that. And also they need to be reusable. So that means you don't have to keep retraining for every single task that you actually, every new task, if it's task specific, it's not reusable. So how do you make it generalizable? So there's a need for generalizable representation learning technique with unsupervised and data efficient learning techniques. I'm really grateful that I managed to watch the first talk today that talks a lot more on efficient machine learning. But in here, my focus is on data efficient learning, which is different. It talks about how much data, labeled data, is actually required in training a model. So and how do we go, what sort of approaches do we need to choose? It all depends on a couple of things. How much of examples you have, and whether you have an annotation in the datasets and how reliable they are. Now, there's some of our key strategies that I'll cover today. First is unsupervised learning, really briefly. Self-supervised learning, which are some of the state-of-the-art work coming from our lab the past 2 years. And if we have time, I'll talk about adversarial transfer learning, but maybe I don't. Talking about representation learning of time series without labels. Now, I mentioned before, if you're actually getting data that you don't actually collect, it could be public data sets, it could be data you collected from public API, census deploy somewhere else, or you might be wanting to deploy a model on the device itself. And the data is actually streamed live. Now, you need to first understand that in terms of understanding patterns, we need to look at where this shape, where the pattern changes in the data, because they might actually indicate a change of class labels or a change of patterns. Now, or it could also indicate anomaly in the sensor streams. there are several, in this paper we have, in input paper, I'll show you the link later. There is the taxonomy that we actually propose, where, you know, the changes are based on temporal. So whether it's not based on statistics or like this gradual sudden changes, but it's more like, you know, based on the shape itself. So the shape could be flipped, for example, here, and the changes could be repetitive or non-repetitive, so completely new shapes or completely new new patterns. And we found there are public data sets that correspond to different types of category of changes. Now, we propose this unsupervised method called espresso. So it's not a coffee brewing method, but it's a way to extract the best information, the most informative information, and to discover the change points. So we extracted there are a couple of steps here. For more detail, look at the paper. We extracted the most similar patterns, and then we actually come up with the candidates of boundary that can actually indicate change points. And based on the greedy search over those boundary candidates, we find segments with the least entropy. And we found, for example, here, this is the most likely change points across this channel. And then we evaluate that. Now, again, one of the first claim I made is we want to make sure the algorithms we come up with are general. So you can apply it to your sensor data without any assumption what kind of data that is. So these are the data sets that we use: hand gestures, physical activity, and then EEG sensors that indicate movement of the eyes, emotion data sets to do with stress, amusement, meditation state. This is multiple sensors. You can see ECG, EMG, EEG, respiration sensors, RFID sensors that's to do with movement, and emotion sensors again here that indicates different pressures. Now, these are again, because this is completely unsupervised, the goal here is to detect changes in class and saying that this is actually a new class, regardless whether it's a class of physical activity of movement or whether it's actually meditation state. And the result of here is we could say, like, we can detect with really high accuracy and really low error across against the other unsupervised methods. Now, so these are also some other extra case studies that we talk about in the paper, where we can actually do this also in real life settings, where we have data when we can detect whether someone's work behavior in their daily routine have changed. We can detect that shift. We can also look at changes in emotion without even knowing the information, domain information about emotion behavior. But then we actually verified with psychologists, and we found that this is actually quite an interesting finding. Now, the code is available on GitHub. Feel free to check it. Now, there's some weaknesses, of course, with espresso, because the thing is, it's unsupervised at the end of the day. We still need to, it also depends on the number of samples that are available. When the data becoming really large, we haven't actually quite validated how good it is to actually handle the huge variability in distribution of the classes. And therefore, we actually introduced something newer, just published earlier this year, where we use contrastive predictive coding, which is a specific type of contrastive learning, which is a type of self-supervised learning, which means we don't need any label data, but we treat it as if this is a classification problem. So again, for change point detection problem, we adopt the idea of contrastive learning. So what is the main idea of contrastive learning? It's been introduced by computer vision domain, where basically we try to minimize samples that they are similar, and we want to maximize those samples that are, we might want to maximize the distances of samples that are different. So we learn from its own sample and as basically a signal whether this is a positive or negative, negatively correlated. Now, our contribution here, we are the first who has done this on time series sensor data. So as I said before, a lot of this work has been done on computer vision, but not on time series sensors. And this is not an easy task, because in time series, we need to look at how do we embed the representation and how do we actually come up with a way that the representation is still general across different type of senses, and we can contrast them. Now, so the goal here is we want to extract representative feature factors from semantic segments to enable change point detection, which can then be used again for downstream tasks like classification or inference. So, for example, here, again, I don't think I have much time left. I'll skip. I'll really talk about this really briefly. So we use representation learning to as a task, as an auxiliary task to do change point detection. So in here, basically, as data coming in stream, either we can learn it in batch manner or online manner. So let's say this is in a batch example. We want to know whether the representation is similar or there's a mismatch in representation. So we want to predict the future of based on the contrastive predictive coding. And we actually make assumption, for example, based on the history, those sensor data that are closer, they will be more similar than the ones further apart. So this is basically the architecture, and we several key contributions in our work is we use negative sampling, and then we have this parallel encoder representation that we actually learn the history and the future representation, and we compute the contrastive loss, and based on that we select the change points. Now, so again, contrastive learning, the goal is to maximize agreement between positive pairs and minimize the agreement between negative pairs. Now, because this is completely not using any label, so we don't know if this is sensor that indicates someone is walking and this is the same, this is another sensor, someone walking and versus running, or maybe this is you know, eye movement, someone is actually blinking or not blinking, for example. We don't know those labels, but we basically just look at the samples, and then we basically mine the positive and negative. So based on the samples, we extract positive and negative pairs, and basically those that are closer, we find them, we say that they are positive, and those further negative. And the architectures we're using causal dialect TCN, and the loss function we're using and influency loss. For more details, while we pick influency loss, is the details in the paper, and you can see the result here. One initial result is the positive pairs that are with history and future without change point. That means they are within the same class. You can see they're actually very similar, and the one that actually has change points, they do actually do not correspond to each other very well. So we can see that our representation is quite effective, and then we basically select the change point based on using cosine similarity, and so we use several benchmark data sets. One is Yahoo benchmark data set, one of the largest data set for anomaly detection, human activity, and their human activity data sets as well. Now, we compare ourselves with a couple of methods, including KLCPD, which was the previous state-of-the-art method for anomaly detection in NeurIPS. Ours actually beat that method, and we also beat our own Espresso method. But as you remember, Espresso is actually much more computationally efficient if you want to try it. But KLCPD, it's actually going to be more expensive in terms of computation, but it's very effective. Now, how do we then leverage self-supervised pre-training? So this is another trick. So one of our recent work published at KDD just a couple months ago is detecting COVID-19 cough sounds with self-supervision. So these there are a lot of activities by a lot of organizations and universities that actually introduce apps, mobile apps, to actually collect cough sounds. And some people actually annotating whether they actually, this is afterwards, after they got a COVID test, whether they actually positive case or not a positive case. But there's a lot more cough sounds that actually don't have any annotations at all. So, so the whole idea here, can we actually use unlabeled respiratory sounds collected on mobile? And can we actually perform contrastive pre-training there? So we just train them once with contrastive manner without labels. And then can we use the downstream phase with, for example, another data set collected by another organization. And then we can classify whether this is actually COVID related or not. So of course, annotated label is very expensive, as I mentioned before. So in here, we introduced a couple of strategy. For example, we introduced random masking, and we perform multiple projection head to before we actually perform the contrastive loss function. And in the downstream classification, based on the masking generator, we then in this phase as well, we can then classify whether this is actually positive or negative. Now, so we pre-trained this on IIS. This data set is collected by IIS Bangalore, Koswara data set, tested on Cambridge COVID Sound data set. Our approach even beat the state-of-the-art VGG-ish supervised method. So it's also beaten transformer-based method. So even without using labeled data, we can perform the classical supervision method. I mean, the state-of-the-art fully supervised method. You're welcome to take a look at the paper for more details. Now, lastly, I'd like to talk about this work. How do we then do self-supervised learning on edge and also on federated manner? So this is a work done by Akib Said from TU Eindhoven. So in this work, we basically look at the whole paradigm of, again, contrastive learning, but doing it on as a local model. And then how do we then actually have it shared as in a federated manner? Now, let's take a look at the step-by-step. First, we introduce what we call Scalogram contrastive network. So Scalogram contrastive network basically is we extracted the wavelet representation into what we call Scalogram network from the same signal. And the other signal, it goes to the signal network. So the same signal, let's say e.g. the same channel that indicates basically within the same channel, we then compare the two. We perform contrastive loss on one that is raw and the other one that has been treated with wavelet transformation into a Scalogram network. We do the same, for example, for other data sets. For example, human active recognition, let's say it's accelerometer and gyroscopes, people running, sitting and all that. Within the same accelerometer channel, we perform this treatment. And if they're actually treated from the same channel, they are considered positive pairs and the rest are negative pairs. So these are just more detail on how the architecture of the raw signal and the Scalogram signal. That's how the Scalogram network. Then how do we actually perform the federated learning? So the central server then actually dispatch the randomly initialized model. And then basically the client basically train the model locally using the Scalogram contrastive network. And then the results are sent back to the server, and basically the server then aggregate this. So of course, this then actually enable more efficient training. Now, these are several data sets that we use: sleep stage, for example, active recognition, device free sensing, and stress detection. As you can see here, there are several results, and even if you can see the fully supervised, these are the fully supervised ones. In some cases, like for example, human activity, our method actually outperformed the fully supervised one, and even it works pretty well in federated settings. So, which means in some cases we might lose accuracy, but not that much. But because you can actually obtain efficiency by learning across multiple smaller devices. What's more interesting when we actually try to learn the SCN representation, so the representation that has been learned with Scalogram contrastive network with TSNE embedding, you could see some kind of like really nice clusters of these different sensor data. Again, we don't use the label. These are actually completely unsupervised, it's completely self-supervised, and you could see clusters form really nicely with this network. And the data is also very effective with low data regime, which means even with the low number of instances, we can outperform the fully supervised ones. So, so the green one's ours, and we can actually outperform, especially those when we don't have much instances. The difference is really huge. I don't have time to cover these. I'll skip directly to here. So We managed to deal with this aspect of bottlenecks requiring labeling, and also this aspect of feature extraction selection requiring domain input by using self-supervised learning. More work needs to be done for multimodal, multi-source data and how to learn over behaviors efficiently, which I didn't manage to talk about just now because I skipped the slides. So I'd like to acknowledge all my students for the great work, and feel free to email me, Flora Salim at RMIT EDU for more details. Thank you.
All right, thank you for the presentation. That was very inspirational.
We especially want to give thanks to our strategic partners, which really helped us that we can make that event possible. So we have first our executive sponsors. We have ARM, which is the Software and Hardware Foundation for tinyML. Then Edge Impulse, tinyML for all developers. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning solutions for tinyML and Edge AI. And our platinum sponsors, Reality AI. They add advanced sensing to your product with Edge AI, tinyML. Then also we have Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence. Seed Studio, the IoT hardware enabler. SensiML builds smart IoT sensor devices from data. SynSense, building sensing and inference hardware for ultra low power embedded mobile and edge devices. And our silver sponsors, we have Aeon Devices, Deep Light, EMSA, Green Waves, Gravity Inc., HOTG, Imagibob, Mob, Geekzo, Rixon Technology, and SAP. So we really want to thank all of our strategic sponsors who will help us. And I hope you all enjoyed it and that we see you again tomorrow. Good evening, everyone.